Oh, hi, Mr. Lee here. All right, so today's mini lesson, we're still going to be comparing linear functions, but more specifically, we're going to be comparing linear functions with non-linear functions. Okay, so we're going to talk about the ins and outs of what makes a linear function an actual linear function, and that should give us some insight also to what a non-linear function is. Okay, so we're going to be talking about the three representations still, the three main representations: graphs, equations, and tables. Desmos actually allows you to visualize all three of them. Right. So we're going to start with an equation here. What makes this equation an actual linear function or a linear equation has to do with the power of x and the way it's formed, right? So you can also see that this is already in slope-intercept form. We learned last semester that's a way to already identify it's a line. Okay, but so if you can write an equation in slope-intercept form, then it has to be a line. Okay. The other indication is the power on x. So right now it's invisible, but if you just treat x by itself, there's actually an invisible power of 1. You could also write it like that, right? X to the power of 1 is just the same as x. We traditionally don't write the 1. We don't need it, which is why it's just 1 half x plus 3, okay? So that's for the equation. For the table, we're looking at your slopes, right? There should be a constant slope throughout, okay? So for example, if I take the change in y for all of these, it's going to be plus 1, right? And I can do it from 4 to 5, you're adding 1. 5 to 6, you're adding 1. Those are all plus 1, right? And then if I go from if I find my change in x, all of these are going to be plus 2. So what I mean by constant is every single combo of points, no matter which 2 points you pick, you're going to get a slope of 1 over 2. Okay, so there's my change in y over change in x. I can even prove it to you by picking any selection of points, right? It doesn't just have to be the first two. You can jump from the first to the last, right? To get from 3 to 6 is a what? Plus 3. And then from a 0 to 6, that's a plus 6. So it's still going to simplify to a 1 over 2, right? Because you put 3 over 6, changing y over changing x, it's still going to simplify to 1 over 2. Okay, so it might look different, but the simplified fractions should give you indication that it's the same number. All right, and then we can even get a little more abstract by adding more points here. So let's choose something. Let's choose another point on the line. Let's choose, like, I don't know, -4 comma 1. So it is kind of strange to jump from maybe this second to last point to this last point, right? But as you can see, we're going to go what? -5, 6 to 1. To get from 6 to 1, you have to subtract 5. But then to get from 6 to -4, you actually subtract 10. Okay, so check it out. It's the same thing. I can do a change in y over change in x. Let's do a -5. Oops, no, I don't want to be there. Let's go down here. I can have a -5 change in y, and then a change in x is -10. It still simplifies to that 0.5 or that 1/2. Okay, so no matter which 2 points you pick on the line, it's going to have a constant rate of change. That's going to be important. Okay, constant slope. If any combo of points proves to have a different slope than any other 2 points, that's going to mean it's a non-linear function. Okay, which we'll get to in a second here. All right, and then the graph is actually the easiest to identify. It's like, duh, it's showing a line, so it's going to be a linear function, okay? So with all that information, you guys can pause, rewind the video as you need. Let's talk about what makes a nonlinear function now, okay? So let me erase some of this. I can keep that, actually. But let me start typing in some nonlinear functions, okay? Actually, I will clear it. Let's see. I will erase all this. All right, so a nonlinear function, let's add a power of 2, right? So y equals x, power of 1, like I told you, that's going to be a line. The second you change the power to a 2, you get all these funky things, okay? So it's going to start curving. So this is nonlinear, obviously. It does not make a line, okay? And then you can even have power of 3. You can even have like 1 over x. So that's the easiest way to actually tell, right? Your equation doesn't have a power of 1, and the graph obviously is not a line, so that's how you can show it. Okay, I would say the hardest piece to identify if it's linear or nonlinear is the table.